Good afternoon. So, I noticed that you uploaded your assignment 1 marks. If there are any issues with it, please feel free to contact me. I noticed Jungyu was actually really nice. All the marks were deducted 0.5 or 0.25 or something like that. But, I think he was overly nice, but as long as he was consistent, I'm okay with it. And if you notice any discrepancies, please come talk to me and we can go through it together. That's the first housekeeping item. Second housekeeping item is that I've uploaded the typed out solutions for preloading and shallow replacement and excavation. So those are on Moodle now. So in case you couldn't catch my scribbles, I think we can read the typeset version quite easily. So back onto our topic. Before we ended last lecture on Friday, we were talking about deep replacement. We just finished our topic on shallow replacement, and we were just going through the numerous deep replacement techniques through excavation displacement. I will record the lecture today and post on the Moodle because of some special requests from students. But I think I still need to follow departmental policy, so I'll try not to keep these on for too long, maybe a week or two. They can't be on there permanently, otherwise, otherwise I'm not following departmental policy. So I'll keep it on there for maybe a week or two, so please watch it before then. And if there are any requests for recording videos, try to let me know a bit earlier. Otherwise, I may not see it in my email before class. And notwithstanding, last class we ended off talking about two types of displacement methods that you see in the top and the middle here in this table. Particularly, these are vibro displacement and vibro concrete columns. And in the field, generally in Hong Kong, we use two terms. We refer to as bottom feeding or top feeding. And bottom feeding is something that we use in Penny Bay for the stone columns in Disneyland, as we'll talk about later. And I'll show you some videos of both top and bottom feeding. So aside from vibro displacement and vibro concrete columns, we also have something called displacement by reverse flight auger. The reverse flight auger is not really a cylinder. It's essentially an auger that can spin in two directions. When it spins in one direction, it can be used to ream, and if you spin in the other direction, you can basically extract the soil that's stuck to your auger. We'll see more details of this later on in the lecture. We often refer to these as controlled modulus columns because, well, depending on what type of concrete you use, you can control the elastic modulus of this material. So this is also called displacement because we're essentially pushing soil aside by rotating this auger and compacting surrounding soil. For those of you that have, this is another housekeeping item, that have sent me emails about the assignment, I usually forward those emails to the TA in charge of marking it. The reason is I don't want the TAs to be giving information to some students and not giving information to other students. So I want the information to be consistent across the board. So the TA in charge of marking the assignment is usually answering your questions pertaining to the assignment. So just to let you know why I'm forwarding the emails to either Fei Hong or Zhongyu. So, sorry, back onto this. So that's displacement auger, and at the bottom left here, we can see that there are sand compaction columns, and this is a quite unique approach because we have to carry out compaction, and it's a replacement technique. With this particular technique, we require vibrating, and you can probably guess that a vibrator is used for granular material. And we'll talk about the limitations of each method for clay-like material and coarse-grained soils, such as sand and gravel. So for this particular method here, you're essentially putting in granular material through hollow casing, and you're vibrating the material to compact it. The vibration also helps you to advance this casing into the hull. So there are numerous advantages with the vibratory component. You can also have something called an encased granular column. These are perhaps some innovative ideas you can think about. For example, can we use recycled plastic sheets to encase stone columns, sand columns, or gravel columns to increase their resistance to loading? So what you see here is essentially geosynthetic encasement. If we can use geosynthetics, which we'll talk about later on in our modules, we can perhaps increase the lateral resistance when this column gets loaded vertically. So we also have encased granite columns and sand compaction columns. Both of these approaches don't really excavate the soil initially. Instead, we try to shove granular material into the ground to push the in-situ soil aside to form our columns and composite foundation. In the middle here, we have excavated technique, which is one of the few rare ones. This is very much conventional. We would use the same techniques for SPT testing, using augers to essentially take up the soil in the ground, excavate it, and then we can either put in granular material, top feed or bottom feed, and if you have a long enough rammer, you can tamp the soil and compact it. So we call this just excavation by drilling using an auger. The last approach that we'll talk about in detail in the subsequent slides is dynamic replacement. Essentially, you apply dynamic loading, which is very similar to deep dynamic compaction that we talked about. And you can imagine that your diameter of this borehole has to be much larger to be able to drop a dynamic tamper into consistent. So this is not exhaustive, but we've tried to idealize and generalize the different types of deep replacement techniques that you can use for ground improvement. Among these methods, probably the most relevant to Hong Kong would be the use of stone columns. Stone can be gravel as well, so we can consider this technique as tried in Hong Kong, particularly for the Benny Bay example that we'll talk about later. But there are also many different types of excavation displacement techniques that you see here that have not been used in Hong Kong. Perhaps these can be used for trials in the future if they have distinct advantages. So, as I've broken down, there are two types of methods. Excavation and displacement. Excavation will generally have less influence in terms of stresses induced in your peripheral soil. The reason is you're not trying to squeeze the soil aside, and you're not inducing lateral stresses into the ground. When you induce lateral stresses, you can get heave in the soil, and you can affect adjacent infrastructure. Excavation techniques are usually more suitable for cohesive soils, and the reason is, one of the examples we showed is a completely open borehole where you need the borehole to be standing on its own. You can imagine if you tried to drill a hole into granular material, it would just collapse, right? So excavation is more suitable for fine-grained or cohesive soil, whatever you like to call it. Displacement approaches generally are more suitable for a more versatile range of both fine-grained and coarse-grained soils, or cohesionless soils. You will induce high stresses, particularly for the one I showed you about dynamic tamping. You're basically pushing the soil down, and the soil will squeeze laterally and induce lots of lateral ground motion. You may or may not be able to handle this type of heave with your nearby infrastructure. For cohesionless soils, you'll definitely get lateral densification compaction. Cohesionless soils, you'll just get a densification effect laterally. You probably don't want to force this displacement approach onto sensitive soils that are liquefiable or collapsible. In our previous lectures, we mentioned some very similar terms. The bottom yellow box here, you can see in a question pressed upon you. Is deep replacement similar to vibro compaction? And is it similar to what we showed you in our deep compaction lecture? Well, there's a slight difference here. As the bottom said, the key difference between vibro compaction and deep replacement is that vibro compaction usually relies on densified in situ soils. Deep replacement, on the other hand, relies on a series of columns to form a composite foundation in the ground to perhaps take some more bearing load from whatever you're trying to build on top. So this is the difference. One, you're trying to form a composite foundation. The other, you're just trying to minimize perhaps liquefaction potential if you're the size of the active area, or just settlement just by compacting it. When we look at the Penny Bay example later, you'll see that for a particular project for land reclamation Hong Kong, we very seldom use just one approach. You'll see PVD drains, you'll see surcharge preloading, you'll see dynamic compaction, and these different techniques are used at different locations along the site, around the site. So even for Penny Bay, which is a relatively small parcel of land, we probably adopt a wide range of land improvement methods. Perhaps stone columns is only a very small portion, where you need to accelerate construction, accelerate consolidation within 3.5 to 4 months, as we'll see later on, because construction program is creating a lot of duress for the engineers. So that's the fundamental difference between excavation and displacement. And we'll go through each of these methods to impress how they look like using videos if we can, and to give you just a mental snapshot of the wide options, tools you have at your disposal if you choose to use deep replacement. Deep replacement is interesting in that if you use coarse granular material, it's almost reminiscent of installing drains in the ground, isn't it? And the main limitation these days for using these type of techniques is, do we have the granular material to put in the ground? So you can think about perhaps more challenges as we talk about it, but we'll break the component or module into excavation approaches and displacement approaches. For excavation, we'll look at vibro replacement, or also known as vibro compaction, and we'll look at rammed aggregate columns as well. For displacement, we'll look at those 6 methods shown at the bottom of the slide. So the first method that we will talk about is vibro replacement, which is an excavation method, and the approach that you'll see here is wet top feeding. Wet means putting wet material in, and top means inserting material from the top. Let's take a video of this. Take a look at this video. So these videos were just extracted by hunting them down on YouTube. There are lots of interesting animations created by various construction companies with specialized equipment. And of course, these are specialized equipment. You would have to hire a contractor. So that's a vibrating probe, and it's wet feeding because there's actually flushing fluid used. You have a jet being constantly flushed into the ground to push out soil, and that's the excavation process. We call this top feeding because you have a bobcat there, or a small excavator, essentially feeding gravel from the top, and it just falls down into the hole. And this probe is being raised and dropped by a very large-scale crane, and as you vibrate, lift it up, and drop it back down, you break the contacts between the gravel, and the gravel can settle. We call this excavation. You can't see it too clearly in this animation, but we call it wet feeding is because the fluid is being flushed out from in the hole, and it flushes out the soil in situ, so you can do that. So let's just take a quick look at this one more time. So in other cases, we also have dry bottom feeding. You can probably guess what that means. So some devices will allow this device suspended by the crane to drop dry material through the middle. And if you drop material from the middle, then the gravel will start from the bottom and come up. So It depends on the approach you want to take, and the obvious limitation here is you need very large cranes to do this, and you need more than one large crane. You're probably limited to some depth as well, because you're trying to break up triangular contacts. So the typical depth we're talking about for these columns is 10 to 15 meters. So you have to assess how thick is your marine deposit layer that you want to improve before you use this approach. It's quite ideal for clay materials because water flushing can really turn the clay into slurry. You can really flush it out of the ground, create a void in the ground. So we've used this approach in Hong Kong for various drainage projects and the boundary crossing facility in Hong Kong. So this is nothing new to Hong Kong. This has been used, and it's one of the potential tools at your disposal as a geotechnical engineer. So again, we want to draw a cross comparison between vibro replacement and vibro compaction. And at the bottom of the slide, we have the particular range of soil where both types of methods would work well. Now, for vibro compaction, you can see you're mostly in the coarse grained material area or the cohesionless material, whereas vibro replacement, where you're flushing material, you want to deal with cohesive or fine grained soils. So that's perhaps the main application for the two types. For cohesive soils, you want to use vibro replacement for flushing material, and for vibro compaction, you generally want to target granular material. So that's the usage for these two types of methods. The next type of excavation method we have is a rammed aggregate column. This method is perhaps not that commonly used. It's limited in depth because we talked about we have to have a long enough ram arm to drop in to ram any granular material that we put in place. So let's take a look at what these rammed aggregate columns look like.
For thousands of years, builders have used an old technique called over-excavation and replacement to address the problem of placing buildings on weak and compressible soils. The process entails excavating and removing a large volume of poor soil where the structure or footing would be.
So this was the over and excavation replacement we talked about, where it's quite costly because you need to do lots of excavation to find lots of fill material. And this video is obviously from some expert or a professional contractor specializing in deep replacement, so that's why they're advocating the use of deep replacement, particularly their rammed aggregate columns. So
replacing it with stronger material and then compacting the better material to support the footing. For projects in which over-excavation was impractical, deep foundations such as driven piles were used instead, an expensive and environmentally insensitive process of driving concrete, steel, or wood into the ground.
they basically said
In the early
everything is bad in
1990s,
their technology is the
Pier
best.
Foundation Company developed rammed aggregate pier systems as an efficient and cost-effective alternative to historically costly and environmentally insensitive solutions.
So as I mentioned, for ram columns, you need to compact the base. So you're often limited in how long your arm can be on your rammer, right? Even for an excavator, you're limited to maybe less than 10 meters, for sure. So if you have a very thick MD layer in Hong Kong, this method might not be so suitable.
Up until now, a consulting geotechnical engineer.
So what they do here, we'll talk to Fox for a bit. So what we do here is we excavate a hole, we pour in gravel, and then we dynamically ram it, and we keep on doing this till we get column top.
Design project that he does, and that is, or does it need to be deep
The
pocket?
construction process utilizes pre-augering and
So the augering is the excavation part, removing soil
vertical
from the
impact
ground.
ramming energy to construct the rammed aggregate pier elements. First, a cavity is drilled according to design specifications, usually 7 to 30 feet. Layers of aggregate are
Now, you can probably imagine this method is not so suitable for sand or gravel material because your hole would not be able to stand by itself, it would collapse, right? So it's more suitable for cohesive materials.
then introduced into the cavity
Then you
in
can dump
thin
sand or
lifts of
gravel,
about 1 foot in
lifts,
thickness.
and
A
compact it with
proprietary
some
and
sort of ram.
patented beveled tamper rams each layer of aggregate using vertical impact ramming energy. This pre-stresses and pre-strains the aggregate at the bottom of the cavity while forming a bottom bulb. Then, thin lifts are incrementally placed and rammed until the pier is constructed. The result is superior strength and stiffness. For sites with soils that are unstable during drilling, or with soils that are contaminated, GeoPier Foundation Company has developed the Impact System, another proprietary and patented rammed aggregate pier method. The Impact
Pretty important, the soil.
Well, more or less, that's how it looks like. I'm trying to sell this more, but there are obvious limitations to this method. You're not going to get very deep improvement depth. So as I mentioned, not good for very thick MD layers. If you have a high water table in the area, you would probably have to dewater first. Or otherwise, it's not very feasible to dump gravel into holes of water. You also need some sort of cohesion in the soil, otherwise your drill holes and bore holes will collapse. So these are in essence the fundamental limitations of rammed aggregate columns. I think these are a bit more time consuming to construct because you have to excavate, place, aggregate in, and also ram. So it's almost like a 3-step method to improve one column. So that's in essence all the excavation methods at hand. The bulk of the other methods for deep replacement really rely on displacement. You're not really excavating a nice hole in the ground and then placing more gravel or sand in. You're essentially just shoving gravel material in and displacing soil aside. Now, you could also argue that rammed aggregate, initially you drill a hole, and then when you ram the aggregate, it displaces the soil naturally. You could also say it's a second stage displacement method. Now, what we see here is going to be vibro displacement, or also called a vibro probe, for dry bottom feeding. And we already looked at wet top feeding, so this is a dry bottom feeding. This is very similar to the technique we use for Penny Bay stone columns. Now, this probe here, if you remember in the previous animation, it had water jets flushing out here. You can also use high pressure air to help you flush some material or cause more disturbance or help the probe go in the ground. The reason this probe can go in the ground is it's constantly vibrating. You're destroying soil contacts, soil grain contacts. And once you reach a certain height in the ground, what happens is now we do bottom feeding. Now to do bottom feeding, that does not mean we have these bobcats or small scale excavators push things into the hole. Rather, we carry out this gravel material to the top of this crane device, and it feeds the gravel material concentrically through this tube. And it goes from bottom up rather than top down. Of course, you can't really see the gravel being put in this animation. It's more or less the same. You do it in lifts, and you keep on vibrating, lifting this probe up and down while it's vibrating, and you form a series of columns and a composite foundation in the ground. So we refer to this method as dry bottom feeding. And again, this is the method you'll see later in our case study. So eventually, one column is built and you get a composite foundation with a series of columns, and simultaneously you'll probably have numerous cranes, numerous probes working in concert with each other. So, we also talked about vibro concrete columns. If you recall, vibro concrete columns, as the name specifies, we don't put gravel in or sand in, we just dry feed concrete in. We don't really use a water jet or anything else to help. So let's take a look at the video. Concrete has the advantage of being more formable in terms of its shape. You have higher strength, you have higher cohesion, you have a higher modulus, higher stiffness. The concrete's also quite expensive compared to just granular material, so that's perhaps a limitation. Here you see the same thing at hand here, except we're injecting concrete from bottom up. And by injecting concrete, in this particular case, you see there's a bit of a wider base. Normally in Hong Kong we call this a bailout. It's to increase the bearing capacity at the bottom of this column. If you are working with piles right now, you might understand that there are two main components with columns, either bearing capacity or skin friction. In this case, we create this special shape to increase bearing capacity of these particular columns, and you would repeat this process until you get a composite foundation of soft soil and concrete columns. Now the typical depth of this is not particularly impressive. You're still working with a relatively thin layer of marine deposit here. Thickness is anywhere less than 15 meters. The construction approach is very similar to what I showed you before. You have a vibrating probe to disturb soil contact, so you can actually push the probe in the ground under its self-weight. And when you get to the depth that you like, then you can concentrically inject concrete into the ground to form these columns. So this is what we have for a vibro concrete column. This technique is very good for cohesive and fine-grained soils. You might not find this so good for granular material. You can imagine that concrete doesn't set right away. So if you have your borehole collapsing, you have granular material collapsing into it, you're not going to get a nice vertical concrete column. So advantages and limitations with vibro concrete columns. Now this is a more detailed view of the reverse flight displacement auger, or AKA also known as controlled modulus stiffness column, and you can control the elastic modulus using concrete of different mixes. What you see on the right here is a typical reverse displacement auger. If you spin it one way into the ground, it acts like a drill, and you can auger into the ground. And when you spin it back the other way, what happens when you're drilling is the soil will get stuck to the auger. And when you spin it the other way very quickly, this soil will spin off the auger centrifugally, and it'll push the peripheral soil in situ aside. And this is the displacement process using a reverse flight displacement auger. This is of course a schematic, and here's a field representation of this reverse flight displacement auger. Let's take a look at this video. Okay, make this better.
The displacement element, more commonly referred to as the bulb, is formed as the diameter of the auger stem spirally increases to the full diameter of the pile.
This is obviously
Once
a
the
cheaper
soil
animation.
reaches the bulb, it is displaced horizontally. All soil cuttings are compressed laterally into the adjacent ground. When the drill is penetrated to the specific tip elevation or depth into the bearing stratum, advancement of tooling is ceased. At this point of the installation process, the drill stem now begins to serve a second purpose, which is that of a trimming pipe used for concrete placement. This provides a favorable ratio between the diameter of the concrete discharge port and the pile diameter.
So for this particular place, you're injecting concrete or grout into the ground. And the advantage of this is it's basically doing the excavation and the displacement together using one device. So that's perhaps the advantage of a reverse flight displacement auger, and we call it controlled modulus because you can use a trimming pipe to put in any concrete strength or stiffness that you like. And this of course has limitations as well. You're probably looking at maybe 15 to 10 meters again in terms of marine deposit depth that you can improve and place some sort of bearing load on top. Some limitations, you're worried again about hull collapse if you don't have casing. High water table, you probably don't want to put too much grout in situations with high water table. But otherwise, the mobilization is considered quite fast, and each column can be constructed quickly, so that's perhaps an advantage. But if you run into hard inclusions in the ground, core stones, This device will not be able to penetrate that, so you have to withdraw and try to put a column in somewhere else. But apparently the controlled modulus is the advantage of this method. The next type of displacement method that we'll look at is sand compaction column. This is another displacement method, and in this case you can install casing. The point of installing casing, anytime we put in casing, we're worried about borehole collapse. That's why it's probably in granular material or cohesive material, because the hole will not be able to stand by itself. So let's take a look at the video here first. So there's two types here. You can either have geosynthetic encased granular columns or non-encased. This is a Japanese example.
The composer method was
Now,
designed to
because we put a casing around our borehole, we can actually go to much greater depth. So you can improve very deep into the ground if your MD layer is very thick, because you have a casing and your hole will not collapse.
repeatedly driven into the ground, withdrawn, and driven down again.
By using the casing as well, you have lots of control about trying to line the casing with geosynthetics as you put it down. So when you retract the casing, you can have a lot more lateral thrust resistance with any geosynthetic. So these columns are very similar to the other methods we looked at, except you have a casing to protect your hole. In this case, you can have top feeding, dry top feeding as well.
That has rewritten the history of ground improvement.
I think this is a lot of,
Sand pile.
Here we go.
A large diameter. It is repeatedly to soft.
there we go.
In the composer method, a casing pipe is
So we put a casing in and it's dry bottom feed.
Then, as sand is discharged, it is repeatedly withdrawn a little at a time and driven down once more to form a large diameter.
So you're slowly taking the casing out of the ground.
Pile in the ground.
Now this sounds quite dandy, but if you have high suction in the ground, it might be very difficult to pull this casing out. It's very common to have very high matrix suction in the ground. Sometimes we put in sheet piles and we can't extract it. It happens in construction. So that's perhaps one of the limitations.
Driven by a vibratory hammer.
You can also have a vibratory casing to enhance penetration into the ground.
When it reaches a set depth, the casing pipe is charged with a set quantity of sand.
You can put in all sorts of materials, stone, gravel, cobble, sand. And here's the casing being extracted in the field. And you can redrive as well. When you redrive, you are polishing as well.
By driving the pipe back down, the sand is
Eventually you form a composite foundation using casing protected
controlled
holes.
in real time. And recorded.
Well, enough of them talking. So advantages, you can go to much deeper depths in marine deposits. Often we use bottom feeding because we have casing to protect our holes. Advantages here, well, it's not so much advantage anymore. You still have problems sourcing sand and stone these days. Construction might be faster and more systematic because you don't have collapse of your hole. That's perhaps the main advantage of this method. Disadvantages, it's sometimes not easy to extract your casing. And there's also a smear effect between the casing and your columns. This might not be easy to quantify or model numerically, if you would like to model stone columns. This method is quite useful for cohesive soils, and cohesive layers are quite thick. So this is essentially the advantage of vibro casing. Your casing can be vibrating or not vibrating. And you can also put in geosynthetics around it if you like. So this is just another specialized deep replacement method. here's the dynamic replacement method using a dynamic tamper in the ground. This is in New Zealand. Now, evidently, you need a pretty large hole to be able to drop this consistently into the hole. And to drop it cleanly into the hole, you probably cannot have very deep improvement depth, right? So that means your marine deposit or clay layer cannot be too thick. And this is probably quite disruptive environmentally, and there's more safety protocols, because every time you drop this, you'll have a very significant PBV, or peak particle velocity, or vibration in the ground. I guess this is near the top of the column, but you can see why you cannot have very deep columns created from dynamic replacement. This method is also not good if you have sensitive soils, because abrupt dynamic loading can liquefy it as well. So it's quite sensitive, but it's quite fast because you're not really doing much except for lifting and dropping, lifting and dropping. So this is the dynamic replacement. And the functional depth is much lower than the methods we mentioned before. You have very large columns, meaning you have to use quite a bit more material. So that's all I want to talk about in terms of the different types of construction methods for deep replacement. Now, what's interesting here is all of these methods are used to form composite foundations. What do we mean by composite foundations? Well, we want in situ soil to take some load, and we also want the columns to take load. If we have pure in situ soil, then whatever we place on top will probably settle, right? It's not strong enough. That's why we try to replace some of the weak in situ soil with stronger granular material. When we do this, we have to pay with some competing effects. If you have too many columns, it becomes too expensive. The ground becomes really stiff though. And it doesn't make sense to install too many columns, because this is just not affordable. You might as well carry out over excavation and replacement. The point of carrying out deep replacement is we don't want to carry out over excavation and replacement because it's too expensive and it costs too much time and money. When we do deep replacement, we have to reach some sort of fine balance. We won't go into calculations and details, but we'll just focus more on concepts. Now, there are of course extreme cases, right? If on the top left figure here, you can see that your columns will be much stiffer than the in situ soil. Anything stiffer will pick up more load. Now, what happens if your columns pick up too much load and the in situ soil doesn't pick up any load? Well, then your columns will fail. There are different failure mechanisms for columns. If it's a concrete column, it can crush in a cone-like manner, it can shear. There are different failure mechanisms for concrete columns as you've learned in your other structural classes. So there has to be a balance as a geotechnical engineer between how much stress these columns take compared to the in situ soil. You can have an equal strain approach. This is what this top left means. What does equal strain mean? Well, it means your entire composite foundation can be designed to settle uniformly. So we know that any replacement column will be stiff compared to the situ soil. So if we enable more stress transfer to the columns, then we'll get more strain. And if we reduce the stress applied to the softer soil, then we can reduce the strain. And there can be some trade-off where you reach an equal strain scenario where this is quite uniform. Now, this is theoretically quite interesting to do, but practically this is not so feasible, right? Often what we have is a non-equal strain rigid loading, where we have columns protruding from the ground, where we have to carry out consolidation and we can trim off the top of the columns afterwards. So this is a very idealized extreme case of equal strain loading. Conversely, you can also have equal stress scenario. Equal stress means you design the situation so that both your columns and in situ soil are subjected to equivalent stress. Now, we can already see what the problem is going to be. The problem is your columns will not settle as much because they're much stiffer, but the surrounding in situ clay will settle more. Under this circumstance, this is actually more realistic of what happens in the field. It's quite easy to deal with this because if your in situ soil has PVD drains and is strengthened, then you can just trim off the top of your replacement columns. Equal strain rigid loading is very classroom, very theoretical, and difficult to achieve. So these are, in essence, two extreme examples. And it's up to the geotechnical engineer to design whether you want to control stress or settlement. If you plan to put some sort of loading on these columns, you probably want to study very carefully what the stress induced on the columns are. Because if they fail catastrophically or brittly, you're not going to have any warning, whatever infrastructure you're putting on top. If you just want to use this parcel of land for maybe a runway, for example, you want to have nice uniform distributed loading, equal strain is probably quite important, right? You don't want any settlement or differential settlement for a runway. Now, how do you control this? Well, you can control this using a few parameters as a geotechnical engineer. One parameter is perhaps you can control the stiffness of the columns. That's very difficult though for stone columns and gravel and sand. It's very difficult to even model numerically using Plaxis. Another parameter you can control is what we call the area replacement ratio. So if you have a unit area of land, how much of this area will consist of columns? The higher your area replacement ratio, the more expensive it is, but the stiffer your ground. So how large is your applied load too? Will most of the load be taken by the columns, or will a lot of the load also sit on the in situ soil? So there are pros and cons that need to be balanced when designing deep replacement methods. We won't dwell too much on this, but you just have to understand the challenges of deep replacement. Now, this doesn't even end here. Now imagine that this method is probably good for just forming a nice parcel of land for maybe a runway. What if we're using this method to try to carry out post-reclamation construction? Now, that's perhaps one of the nightmares we'll face, right? What if you're trying to build tunnels in this, you're trying to put box culverts in here, you're trying to excavate in this. Now, how do you excavate in a composite foundation? What are we worried about? What type of failure mechanisms are we worried about? We probably have to consider the tensile strength of these columns. We're probably worried about, okay, so soil we're quite familiar with when we carry out Plaxis, but what kind of material model should we use for these composite columns, right? Does it behave like concrete? Is it very flexible? These are perhaps some of the issues that we need to cater for. And these are some of the problems we're facing now. When we carried out the reclamation of the third runway system, although it wasn't deep replacement, it was deep cement mixing. We'll talk about chemical means later, but the same concept is used where you put lots of columns in the ground to form a composite foundation, and then you put the runway over it. Now this is great for rapid construction, right? We want to use the runway quickly, and this will help you achieve that. But one of the main concerns now is, what if we start using composite foundations for post-reclamation construction, excavation, foundation? Do these columns contribute to any resistance if we want to build a skyscraper on top? So how do we cater for this, right? If we're using these types of composite foundations for probably a much more complex means than it was intended for. we saw a lot of success with deep cement mixing for the third runway system, and now we're trying to apply it for other parcels of land. In Dongchong, Malusui, right, Longbutan, these are the places we're trying to reclaim using DCM. But then the land usage issue, it's quite different, right? We're not building a runway on top of these things. We're trying to build residential towers, maybe temporary construction structures underneath. So how do we deal with this? How do you cut into land afterwards? Does it look stable? Does it behave like a bunch of soldier piles maybe as a retaining wall? These are probably aspects we don't have so much experience with, let alone what type of factors of safety we should use, what type of material we should use. These are real challenges that we'll face if we try to create too many composite foundations for post-reclamation construction. So these are some aspects you can perhaps talk about with your geo examiner if you're brave enough. Yeah, real problems at hand here using these methods. So just food for thought, I guess. There are different ways. Just to let you know, putting columns in isn't the end of the story. What do we do afterwards, right? So anyways, for this slide, we're not even talking about post-reclamation excavation for construction. We're just talking about how to distribute loading, how we can transfer stress to in-situ soil and columns. Now, there are of course different methods you can impose. You can use unit cells to calculate, don't worry, it's not on your exam. Different methods to look at. After I say that, everyone puts their pen down. So we're just talking about whether we have some sort of modulus to describe the composite ground. It's easy to describe the stiffness of a material that's the same, but what if you have two types of materials within a unit cell? How do you describe the modulus, right? Without being able to describe the modulus, how do you design for settlement or stress that this particular parcel of land will take? So we often use some concepts here that you see. Unit cell, stress concentration ratio. Stress concentration ratio means how much stress the column is taking relative to the in-situ soil. For granular columns, you can see at the bottom, probably the most useful piece of information. We have stress concentration ratios where the columns take 1 to 5 times that of the in-situ soil. For concrete columns, these are much stiffer. You're going to have less movement. These columns take 10 times the stress compared to the in-situ soil. So the case I showed you where you can get uniform settlement, that's a difficult case to achieve. And you can probably look at different cases. What I just showed you is a unit cell for a one-dimensional case. If you have 3D scenarios, you probably need to do 3D analysis. So with a lot of these new ground improvement techniques, we're finding that we're having to revisit Plaxis 3D to look at different types of stress concentration ratios and to try to predict the settlement with time. So this is just food for thought, some information you can look at your own leisure. And of course, there are different ways to calculate how much stress and what's a unit cell. So this is just an example at the bottom of how you can decide the area carried for the design of a unit cell. And if you remember, for PVD drains, we always deal with unit cells. Similar concept with deep replacement. We want to deal with regular patterns, so you would need to carry out stress analysis for this as well, although this is well beyond the scope of this class. So just more food for thought. And these, of course, are just more information, bonus material for you if you want to understand how to look at deep replacement. For me, I'm happy if you understand that there's two types of methods, excavation and replacement, and the various types of methods like dry and wet top feeding. The worst case scenario is I asked you what's the difference between vibro displacement and vibro compaction, something like that. Conceptually, for this module, we won't have to worry about any unit cell or stress calculations. I just want to explain to you that it's not as simple as what I showed you, a video of making a column and then that's it. We have to calculate the stress distributed to the in situ soil, and that distributed to the columns. Now, more importantly, I probably want you to know what are the potential failure modes of composite foundations. This slide shows the case where your columns take too much stress. If you have a concrete column, you can end up crushing it. If you have granular column, you can get generalized bearing capacity at the top of your column. It's very much like a shallow replacement, right, in the middle. You can also get punching failure. It's just like shallow replacement. It's no difference except you're looking at a much greater depth. So these failure mechanisms do occur, right? And you do have to check for these potential failure mechanisms, right? And we often do this using Plaxis because you can reveal many of these mechanisms in one go using Plaxis. So another one is bulging. If you don't have sufficient lateral stresses confining your column, you can get bulging, and bulging will happen at the top of the columns where you have much less confining stress. So these are potential other columns, and this looks dangerous. Someone wanting to connect here? No. Okay, so we'll carry on with our case study in next class, and then we can switch on to our next topic. So thanks for your time today.